All right, so we are back in section 2.36 about doing Bayesian inference for the Gaussian. In the previous section, we talked about a situation where the variance was known and we were estimating the mean. And now we're going to do the other way. So the mean is known and we want to infer the variance. And the idea is going to be the same as before. So we need to bring a prior distribution into the game. And the one we're going to use is what's called the conjugate prior. The conjugate prior is such that when you multiply by the likelihood, the posterior is in the same family as the likelihood. So we're going to see how to do that. Okay, so our calculation will be greatly simplified if we choose a conjugate form for the prior distributions. And it turns out to be convenient to work with the precision 1 over the variance. So we're not going to be talking about the variance itself, but 1 over the variance. The likelihood function for lambda takes the form. So remember we've got n in independent random variables, observations, and so we can just multiply their probabilities, and they're all Gaussian. And instead of the variance, we're just writing things in terms of precision. So the lambda to the -1 is the variance, basically. And then when you write this out, there's some normalizing terms, but then you get the precision to the power of n over 2, and that's the same as the thing that was showing up in the bottom as 2 pi sigma squared to the so-and-so. And then you get the precision showing up again in here inside the exponential. You would normally see this as 1 over 2 sigma squared. So when you talk about precision, it actually shows up on top. It's linear in the data points rather than being 1 over it being linear. Okay, and so now this is the form of our likelihood. So now we say, well, we want our prior to kind of be, if a prior looks like this as well, its prior is going to be a function of lambda. Then when we multiply things together, then the posterior will look just like that. And so that just leads us to the gamma distribution. So it says the corresponding conjugate prior should therefore be proportional to the product of a power of lambda and the exponential of a linear function of lambda. So as you can probably see, this is the power of lambda and then a linear function of lambda. So lambdas are showing up on top and then multiplying some junk in here. We don't care about that. We're just going to say it's just we're going to just call this some number. I don't know, it's going to call it b. Maybe it's, again, absorbing the 2. So basically all that stuff that's showing up in there, we're just going to say that's going to be some parameter, some value that we can adjust. And we're going to have some power of lambda. So here's n over 2, but we're going to have some arbitrary power. And so there we go. So we got gamma blah, blah, blah is going to be equal to, there's our power of lambda, and our exponential, which is linear in lambda. So this is the gamma, the very famous gamma distribution. The gamma distribution is a very good one to know about. It's very versatile. So here are some pictures of it. You can, by adjusting the parameters, you can get all sorts of different forms from it. It's really useful for modeling positive values. It has lots of really nice properties. You get the exponential distribution in the case where a is equal to 1. So this is just an exponential distribution. If I recall, I think as a becomes very large, it ends up becoming a Gaussian. You can also get these kind of heavy-tailed behavior where it has lots of zeros, but then gets lots of maybe some large values as well. So it's a really good one to know about. And so as we're finding out, one of its uses is as a conjugate prior for when we're estimating the variance or the precision of a Gaussian distribution. Okay, so here gamma a is a gamma function and it ensures that it's correctly normalized. Okay, and we won't have to worry about too much about any of the normalizations here. The gamma distribution has a finite integral if a is greater than 0, and distribution itself is finite if a is greater than or equal to 1. So you see here, up here, you see a is less than 1, so you get this interesting, can be very useful peaky behavior at 0, but if a is at 1 or greater, then it will have finite values, so it doesn't blow up to infinity. Sometimes you want it to blow up to infinity, so don't think that that's like a bad thing. It's actually part of the versatility of the gamma distribution, I would say. Okay, and the mean and the variance are given by this, how they're related. Now consider prior. Okay, so now consider prior distribution gamma. So we just said, look, we picked our conjugate prior, and we're going to pick these parameters a0 and b0. And now we're going to try to interpret what these mean in terms of how they get updated, which is actually kind of cool. So if we multiply by the likelihood function, so that was what we had up here. Then we obtain a distribution, so we get the lambda powers multiplying, and then you get something going on in there, right? So now you just, so we're going to group them separately. So first we're going to look at what happens to the lambda powers. So we say, oh, it's like, we recognize there's a gamma distribution of the form. So again, we're in the same family, right, by design. So we have a power of gamma times something that's linear in gamma, right? There's gamma times, the lambda, sorry, I keep saying gamma, lambda. It's kind of confusing because it's a gamma distribution, but the parameter here is lambda. Okay, so I'm talking about these guys. So it's linear in this guy because it's lambda times b naught and lambda times all this junk. So we recognize the gamma distribution of the form gamma with these parameters. And what are those parameters now? Well, the power has gone from, it was supposed to be something minus 1. Well, the something now is a naught plus n over 2. And what's happening with bn? So bn is everything that's multiplying lambda, appropriately scaled. So we've got the b naught plus, taking care of the minus sign, plus 1/2 times this thing. And what is this? Well, if we write this term as times n, then this thing just becomes your maximum likelihood estimate of the variance. So that's pretty cool. So it looks like when you get n observations, your a naught goes up by n over 2, and your b naught goes up by something proportional to variance. So it looks like a naught represents, you can think of it as kind of a number of observations parameter, and b naught is kind of your variance parameter. Okay, right. Note that in 2.149, there is no need to keep track of the normalization constants in the prior, because if required, the correct coefficient can be found at the end using the normalized form of a gamma distribution. I think all he's saying there is, look, if you know what a and b are, which we are figuring out, then the normalizing functions are gamma a and b to the a. So you don't have to worry about them. And our parameter, when we're estimating these parameters, they don't really, those normalizing terms don't come up. Cool. So if we need them, we can always just plug them back in. Okay, from 2.15 naught, so this thing, so we're trying to get the interpretation, we see that the effect of observing n data points is to increase the value of the coefficient a by n over 2. Thus, we can interpret the parameter a naught in the prior in terms of 2a naught effective prior observations. So it's kind of like saying, well, if I multiply this by 2, I get the number of actual observations. So then that means if I multiply this by 2, that's kind of my fictitious prior observations. So that's pretty cool. Similarly, from 2.151, we see that the n data points contribute n sigma ml squared over 2 to the parameter b, where sigma squared ml is the variance. And so we can interpret the parameter b naught in the prior as arising from 2a naught effective prior observations having variance so and so. So as arising from 2a naught effective having variance, right? So you're just essentially saying that, look, so we can just kind of interpret this thing in the same way. So so we can say, well, so b naught is now supposed to equal to, we're just following the same pattern as this. It's supposed to equal to our effective number of observations divided by 2. So that's divided by 2 times the variance of the prior variance. And so in that case, so therefore the prior variance is going to equal to b naught over a naught. So we can kind of, all he's saying is you can interpret b naught as being like you have 2a naught observations of a variance sigma naught squared, which is that. So recall that we made an analogous interpretation for the Dirichlet prior way back when. These distributions are examples of the exponential family, and we will see that the interpretation of the conjugate prior in terms of effective fictitious data points is the general one for the exponential family distribution. So that's pretty cool. Okay, so that's cool. So that's kind of the end of inferring the precision. And I was just looking at the time to see whether we should just go on, I think, to the next section. And I think we might as well do that because I think there isn't that much left. So instead of working with the precision, we can consider the variance itself. And so if we do that, we work with the inverse gamma distribution, but we're not going to work with that anymore. Okay, so that's the end of that. And so now we're going to come to this final section where, let's highlight that, where both the mean and precision are unknown. And so we're going to play the same game. It gets a little bit trickier because I think at least to me it's a little bit less obvious how to pick out the what to make the conjugate prior. Both the mean and precision are unknown. But we're gonna try playing the same thing. Okay, so first let's look at the likelihood function. So now it's a function of both mu and lambda. All right, so and let's look at the terms that show up in it. So this is, again, these are going to be the exponential terms coming from these are, each one of these is just going to be the Gaussian terms, right, contributing. So you've got the data points minus their mean divided by their variance or multiplied by their precision, and then you've got the normalizing constants outside, and you're multiplying all of them because, again, your data points are independent. So now he kind of groups them in a certain way. And again, it's not clear to me why you would pick a particular order. I have kind of a couple of guesses for this. One is, if we're looking ahead to kind of the exponential family stuff, you might want to group them by terms that contain what are going to become your sufficient statistics. So the terms that sum up your data in different ways, so summarize your data in different ways. So this is kind of a term that has the data, and this is some kind of independent term. Another way is you could maybe look for the ways the different parameters are showing up. So it looks like, for example, here we don't have any mu terms. Here we have mu showing up in linearly, so just the power of 1. And here we have it showing up as a power of 2. So maybe that's kind of how you could kind of pull that apart. But okay, so let's say you've kind of pulled it apart that way. So now we now wish to identify a prior distribution that has the same functional dependence on mu and lambda as a likelihood function, and should therefore take the form. So what are we saying? Well, we've got this thing to the power of n. So okay, so let's just copy that over. We say it's gonna, and notice there's no data in this. So we've got lambda to the 1/2 times, exactly the same, but maybe we can raise it to some. It doesn't have to be integer, just some power beta. So that's one of our first parameters. And then we've got a separate thing showing up here, which is an exponential of a linear term in lambda mu, and then just a linear term in lambda. So this is all linear in lambda. I know it's x squared points, but as far as you're concerned, those are just a bunch of numbers. So you just add them all up, linear in lambda, and then multiple of lambda and mu. So this makes me think that actually the way you want to do it is you want to group them by their dependencies on lambda and mu, because that's kind of what you care about. Okay, so then we just kind of split that up. I don't think he's done anything else. He's brought the lambda on the outside, and this b is kind of gone on the inside, so it's going to be b. I think he just rearranged things, I believe. Where is the d coming from? Yeah, I think he's just kind of, so I think what he's done here is just rearranged things so that you can get a term that has only lambdas in it. And then he's got a term that has lambda and mu in it. Just rearrange that equation. And the reason why he's done that is because you can write this joint probability distribution, just using, I guess, the product rule or whatever it was, as the product of p lambda times p mu given lambda. So p lambda is just something that involves just lambda, and that looks like a gamma distribution. And then you have a Gaussian distribution, right? You have something quadratic showing up there. Okay, so I think it's kind of a few steps that, I think, yeah, maybe you just have to be clever to know to look for that. Maybe you get good at it with practice. I've never done it, so I'm just seeing it as the first time with you guys as well. It doesn't seem too difficult, and I think if you just kind of played around with it a little bit, you could come up with it as well. Okay, so now we see that p mu given lambda is a Gaussian whose precision, so this thing, is a linear function of lambda. And so that's going to be beta lambda. And p of lambda is a gamma distributed. So remember, lambda does something times exponential decay in lambda. So the normalized pi takes the form, the product of a normal distribution and a gamma distribution, where you've now defined some constants, so on and so. This distribution is called the normal gamma or Gaussian gamma distribution, and is plotted in figure 2.14. So that's kind of what it looks like for a particular set of parameters. Can't really give you too much intuition about that. Yep, so let's just keep going. Note that this is not simple, note that it's not simply the product of an independent Gaussian prior over mu. So I think that's kind of an important point. So let's just not simply the product of an independent Gaussian prior over mu. Right. So and the reason why that is because the precision term is showing up inside the normal distribution. Right. Even if we chose a prior in which mu and lambda were independent, the posterior distribution would exhibit a coupling between precision of mu and the value. So he's just saying that, look, even if you originally maybe got rid of this dependence you just got initially in the prior, then as soon as you bring in the likelihood through the data points, then the result would have some kind of a dependence showing up like this, so some kind of a complicated dependence. So you're all of a sudden your distribution on your means would now involve the the lambdas as well, your precision as well. So you would only last for one step. Okay, cool. So that's that, and then we're just going to look at kind of some generalizations of this. I don't know if we're going to actually work with any of these these higher dimensional distributions. Maybe later on when we talk about linear models, but let's just touch on them. I'm not going to say anything beyond what he says here. I'll just tell you the ones that I have heard of. For example, the Wishart distribution is one I have seen. Also, the inverse Wishart distribution as priors on covariances and precisions, which is I think what he's talking about here. So let's just talk about that. So in the case of the multivariate Gaussian distribution for a d-dimensional variable, so we've been working with one-dimensional variables, the conjugate prior distribution for the mean, assuming the precision is known, is again Gaussian, which I think there's an exercise on that you can do. It should be easy. But for known, mean, and unknown precision matrix lambda, the conjugate prior is the Wishart distribution given by this expression, which yeah, we're not going to go into it much, but let's say nu is the degrees of freedom, W is a d by d scale matrix, and trace is a trace. Okay, normalization constant is whatever it is, some big complicated thing. Also possible to define a conjugate prior over the covariance matrix itself rather than over the precision matrix, which leads us to the inverse Wishart distribution. Although we shall not discuss this further. And then if both the mean and precision are unknown, then following a similar line of reasoning to the univariate case, the conjugate prior is given by, again, you've got this product of a Gaussian that depends on the precision times a Wishart distribution on the precision. So yeah, so I think I've heard about the Wishart and I've heard about the inverse Wishart, and this kind of comes up with again doing kind of Bayesian inference. If you're working exactly as here, like you've got some covariance and you want some prior on covariances, then you want to work with the inverse Wishart. If you're working with precisions, you want to work on the Wishart distribution and kind of updating those parameters. But I've only, I think, worked on them very briefly a few years ago. So maybe good ones to just know about in case you're solving similar problems. And I expect we'll see more of them as we go. Maybe later on we're working with linear models and things like that. Okay, but I think that's enough. That's the end of this section. So hopefully that was useful. I mean, I think there were some kind of interesting tricks of how to come up with the prior distributions, the conjugate priors. We learned about how to interpret the distribution of the gamma, the parameters of the gamma distribution. The gamma distribution itself is very useful. So I would become familiar with it. It's very versatile. So get to know it. And yeah, I think it's actually quite cool that it can come up here and then you can get an interpretation of what these parameters mean through the way they're updated with data. So I think that's kind of a cool way. Often when you're given these parameters, like when you're given a gamma distribution, I think one of them is like a scale, one of them is called a shape parameter. And okay, it affects the shape. I think maybe A is a shape parameter. But what does that actually mean? Well, this kind of gives you a little different insight. It's like, well, A is actually like your effective number of parameters, and B is kind of like your variance, your variance parameter somehow. So that can kind of give you a different perspective on the distributions you're working with, which I think is really cool. Good, I think that's all I wanted to say. Hopefully that was useful for you guys. So please let me know if it was or if it wasn't. If you found any mistakes, etc., please share them because you don't just help me, you help anybody else who's watching these videos. So just post in the comments directly. Yeah, and hopefully I'll see you guys next time when we'll talk about the student's t distribution, which is very cool. Okay, so see you then.